Okay, I was asked just a moment ago to chair this session. So let's start with the afternoon session. The first talk is by Vitev about radiative processes and jet modification at EIC.
Okay. All right, so let me thank the organizers for the opportunity to talk about this type of physics at the Future Electron Ion Collider. So the outline of the talk, the plan for today, is to show you that there is a renewed interest in particle and jet production in semi-inclusive DIS from like a wide community that has not traditionally been involved, associated with like nuclear physics, or JLab, or future EIC, or RIC studies. I'll discuss briefly the status of in-medium calculations in SIDIS as they were presented in the last white paper, and I want to point out what's missing. I think we've made a lot of progress, and like in a real future white paper, in a real future program, I think it would be very valuable to include this. I'm not talking about brief 10-page papers to serve specific purposes, but for real science. And then I will discuss the status of in-medium radiative correction calculations and how we can make use of them, the new techniques for particle and jet production in nuclei, the way in which we can implement those in-medium radiative calculations. If I have time, I'll touch on event shapes at the IC and how this can help us constrain the strong coupling constant. I'll come to the conclusions. Now, this talk will have a technical part to it, and a lot of the credit for this work goes to my collaborators, but most recently what I'll talk about is work done with Matt Sievert on the analytic side and Barbara Muon on the numerical side, the implementation of those in-medium radiative corrections. So let's go to the introduction. I'll start with this slide. You've seen this ad nauseum by now. But let me tell you my perspective. A few years ago, the long-range plan recommended the construction of a luminosity powerized EIC as the priority for EFRI, and this kind of restarted things, but they were a little bit on the back burner until the National Academy of Sciences report came. And that it came with a strong endorsement, but also with a number of observations. And a lot of it talks about that this is an inclusive facility. It talks about its importance to the US leadership, but also how its physics ties to other fields. And we are trying to bring support and interest through other fields of science. And by doing that, we should not forget that we should also be inclusive about the broader high-energy nuclear physics community that has already worked on this. And that would be one of the topics. I think it's realized that there are serious gaps into the EIC program related to the topic of particle and jet production. And this is what I would like to talk about. Now, here are some of the calculations from people who are seen as traditional perturbative QCD theorists. Some of them you know. This is Patrice Hinderer and Werner Vogelsang. This is an excluding order calculation done a few years ago for high-PT Hadron production at the Future Electron Ion Collider, where they show the accuracy that can be achieved, how next to leading order corrections compare to the lowest order result, and what is the Weizsäcker-Williams, the result Fulton contribution to the process. All of you, of course, know Werner, but perhaps not all of you are aware of other work that goes in this direction by people who are traditionally funded by high-energy physics. This is the work that comes from soft collinear effective field theory, and this is the group of Raja Boghezau and Frank Petriello. What they did using novel techniques that include androgenous subtraction, they were all able to even go to next to leading order calculations, and you kind of see, they agree of course with Werner on the size of next to leading order corrections, and you can judge for yourself what is the role of next to leading order corrections there. And they also calculated up next to leading order the double longitudinal single spin asymmetries at the Future Electron Ion Collider. Here is the predicted asymmetry, and you can even see that the result photo production really does not contribute all that much to those asymmetries. So such calculations are very important, not only because they are the most accurate calculations that will help us pin down perhaps the Parton distributions, their modification nuclei, but they're also a baseline to look for nuclear modifications, starting from cross-sections and to their substructure. Now, what do we know from heavy ion collisions where we don't have a single nucleus, we have two nuclei colliding, and we hope that we may produce a medium, a deconfined medium called coronal plasma. What we know that in the modification of Parton showers is the corner of high-PP physics. And these effects are significant, and they're largely not related to initial state effect or Parton distributions. So I'm showing a few examples. Let me explain why. This plot was one of the earlier plots that came from the relativistic heavy ion collider around 2004. And what you see here is a factor of 5 suppression of particles that can interact strongly in the final state, such as pions and matters, and at the same time, you see that direct photons, which do not interact strongly, undergo no modification. It is very clear that this is not a nuclear PDF effect or a small X effect. It's related to final state interactions. We have seen such modifications in a myriad of observables. The very large suppression at the LHC of heavy flavor production, B-jets. The substructure of jets is also modified, as shown here. And once again, this cannot come from something that can be incorporated in Parton distributions. In fact, all nuclear metal effects, as is explicitly shown, really do not modify the substructure of jets. So these effects are large, and we expect such effects will appear also at the electron-ion collider, and this will be something valuable to incorporate in a future program. So let's see what is the status now of what we have in existing white papers and which propagates into long-range plans. The two topics that are conventionally mentioned is the study of hadronization, the possibility of hadronization inside nuclei, color transparency or lack thereof, and also effects of energy loss in nuclear matter as stimulated and kind of shown by the measurements of Hermes at the beginning of this century. So this is circa 2000 physics. It is very important to understand better, but also we kind of have to move forward. It's been already 20 years. Let me explain the ideas behind what has made it so far in the white paper. One of them is based on the possibility that when we have semi-inclusive deep inelastic scattering, a hadron is formed in two stages. There is a pre-hadron formation, and then there is a hadron formation where the Q-bar pair does not interact in the nucleus. Those models are associated primarily with the work of Boris Kupeliovich, and he can model those lengths, the pre-hadron formation and the hadron formation length, to obtain a description of the suppression of semi-inclusive hadron production at Hermes as a function of the momentum transfer mu or the fragmentation fraction C. What I find interesting is that it can provide some insight into the particle species dependence of the attenuation. But I also worry that for really light particles like pions, those formation times might be underestimated. Those are significant boosts, and I have hard time seeing how the pion and the proton can have similar formation times. So the other models that have been proposed are based on radiative energy losses. The idea here is the following. The struct quark propagates through nuclear matter, similar to the case of Parton propagation in the QGP, and it loses energy through radiative processes. In this case, the suppression observed by Hermes can be related to an effective modification of the fragmentation functions for the radiative energy loss processes. And what I show here is a set of calculations by Francois Rion, who fits the data with radiative energy loss formalism in an infinite medium with a transport parameter, that is momentum transfer squared per unit length, of about GeV per Fermi. Those are typically very large transport parameters for nuclear matter, and this is typical of infinite medium approaches. I'll comment a little bit about this later. Similar but competing picture is given by the group of Shinya and Langin collaborators, who also fit those data using radiative energy loss approaches. I've shown here explicitly what I mean by effective modification of the fragmentation functions. This is the probability to lose energy, and this is the kinematic modification that one can derive. And it also gives a very good description. In later works, they've even included some in-medium evolution at very high scales. Still, I believe most of the effects come from radiative energy losses. Now, what you will notice, however, is that the transport properties that they extract are just 0.02 Jeff squared for Fermi, to be compared to about 1. And there is a factor of 30 discrepancy in the extracted properties of cold nuclear matter between the two approaches. So this is something that is not resolved, and this is something that we have to address again at the future electron ion collider.
Is this the same data?
Oh, that's exactly the same data. Yep. Yep. So, I mean, the story is the same as, I'll tell you what I think later. I think this underestimates, my personal opinion. I think based on infinite BDMPS approaches, overestimates it. I don't know why she underestimates. I think I understand why infinite approaches overestimate it. But in my opinion, that's also way too small. Okay, so we have those serious unresolved discrepancies. And again, those type of studies are already almost 20 years old. So hopefully we can make some progress. But what else can we do? Kind of in addition to looking at the suppression, we can perhaps quantify some other properties of nuclei, not only better constrained transport properties, but also the radiation lengths. Now, when we talk about particle propagation in matter, we go back to QED, our normal interactions that we're familiar with. What we show here is simply taken from the particle data book. This is the stopping power of copper for muons, and those stopping powers are known to about 2% accuracy. We don't have 30 times uncertainty. One way to constrain those is to look at proton-nucleus collisions. And what is observed as we go in Drell-Yan production to large Feynman X is that there is a suppression, which in the past has been interpreted possibly due to shadowing, but possibly due to energy loss in nuclear matter. And so that was not possible to resolve. There is a new experiment in 906, which works at a specific center of mass energy. And if we kind of plot the shadowing parameterizations at the time, they give very little modification. This is the black dashed line. And if we include energy losses, and these are the typical radiation lengths, on the order of about 100 Fermi, we get significant suppression. And this is one way in which we can constrain the radiation lengths of large nuclei. Another way in which we can do that is, of course, to do similar measurements at the EIC and see if there is a consistency between those two measurements. So there is another program in understanding the stopping power. I'm more interested in understanding the stopping power of large nuclei rather than their transparency, for which we really haven't had much evidence so far.
Sorry, what is X0 again?
X0 is the radiation length. So this is the distance. This is the distance of material in which it will lose like about, I forgot, E or 1/e kind of fraction of its energy, the particle. So in other words, like the nucleus is about, in a diameter 10 Fermi. So a nucleus is about 1/10 of a radiation length, so to speak, right? And this is really all that's needed in order to get the suppressions that one can potentially measure, right? Okay, we don't need all that, yes.
Here, I was always confused in this final state interaction. Which part is going into distribution and which part is going into fragmentation? When you have this after scattering, the final state interaction.
Okay, so that's Drell-Yan, that's initial state.
No. I was asking about their Machinian description of the Hermes data.
So this is final state interactions, and the final state
sometimes since they had both versions. So in one case it was kind of modification of the fragmentation part, and in the other case they put this final state interaction into the modified TND. What was
I'm not aware what they did with the medium modified TMD. I mean, this is definitely like final state interactions, which they put in the fragmentation functions, which I think is the correct thing to do. I'm not aware about what they did. I know that you showed kind of a broadening that can come from multiple scattering, but I'm really not familiar with that particular paper, if there's a paper, or maybe it was a private communication.
Just if I remember correctly, these frameworks are treated the same way. To them, it's the same thing. They don't really separate.
Okay, I don't know what, let me restrict myself to the things that I've looked at and that I know. Okay, so.
Sorry, Ivan, again, on that previous slide, millimeters?
Yeah, that's good.
Oh, so what I wanted to say is that, like, for the heaviest nuclei, for the large Z materials, this is what determines the stopping, right? It goes, I think, is Z to the square, at least. The shortest radiation lengths that we know are about 0.3 Fermi, if I remember correctly. The radiation lengths that we are talking in nuclei are, 0.3 millimeters, are about 100 Fermi. So that's about 10 orders of magnitude difference. It's quite significant. I mean, it's like if this can be pinned down, it would be very interesting, I think. It was to emphasize, right, minimum means, the shortest radiation lengths. I'm not interested in large radiation lengths. I want to make the point that in nuclei, it's 10 orders of magnitude shorter. So that's the point of this cryptic.
It's QED, not
Yes, yeah, of course. That's the point of this cryptic line, which is not very well written. Right. So, okay, so now let's go to the status of in-medium radiative interactions. And there has been a lot of work on those radiative interactions. Going back now, it's probably 30 years, like almost 30 years. There are typically two types of approaches. One of them assumes that the medium is infinitely thick. And this does lead to certain simplifications. It allows to some correlations between multiple scattering centers and obtain expressions, that are relatively short, kind of that they're convenient pocket formulas. But there are also problems, some questions that arise with that, like a realistic nucleus. In a realistic nucleus, a quark probably scatters, or in a QGP, if you use thermal field theory, would scatter on the order of 2 times, even if it starts from the center. And gluons also scatter about 5 times. So the infinitely thick medium may not be a good approximation. But what I did not realize, and what was pointed out by Fell and Vasquez just very recently, is that by taking an infinitely thick medium, one actually misses important diagrams that contribute to the branching in the realistic case. That would be initial state interaction, final state interaction, as well as the interaction with the nucleus. Kind of this result is, I'm sure, known to people who work in small x physics. The nucleus will just act as one coherent source of radiation, and it will produce a Birch-Gunnian radiation determined by the saturation scale. But if we take this infinite medium approach, where those diagrams are missing, we're just going to get 0, strictly in the high energy limit. It was really pointed out very clearly in this figure. What Fell and Vasquez did is they did a numerical simulation of all the diagrams that contribute to the branch-through, and then they obtained this spectrum. And then they also showed that if they ignore, just neglect the initial and final state radiation and the refraction, they're going to obtain this purple line, and you see how the intensity spectrum dies away completely very quickly, as opposed to having this kind of normal behavior that one expects to obtain. And of course, this is the limit in which those thick medium approaches work. Of course, one can still take them and do phenomenology, try to fit data, and this can be obtained by increasing a lot the transport properties of the medium. And I think here lies one of the reasons, one of the main reasons for which there is a significant difference in the transport parameters obtained when you use like an infinite medium approach versus the transport parameters when one actually includes those other diagrams in the calculation. So I think that's kind of one thing that I learned only very recently.
So can I ask a very
Sure.
uninformed or naive question? Going back to the QED alternative, could I think about this as transition radiation?
Transition radiation, I think, is like on the boundary, when you go on the boundary.
So it's very much a finite.
Yeah, no, I don't think so. Like, I think that's the Terbi-Cayley effect, and there are subtle differences.
Okay.
I mean, this really qualitatively changes the behavior of the spectrum, right? It kind of misses all the radiation, which makes a rapidity plateau, or it's kind of approximately uniform in rapidity distribution radiation. Now, on the other hand, one can also do finite, what is known as finite opacity approaches, and build an expansion in the correlation between those multiple scattering centers. Kind of, in a sense, what those people did numerically last year, but that has been done analytically for a while. And one can organize this in classes of diagrams formulated in terms of a recursion relation, in terms of an operator, and so for a number of cases. This was done first by Gelasi and collaborators back in 2000. It was also done first order in opacity, kind of the lowest non-trivial correlation between scattering centers by Shou-Feng Guo and Xinyan Wang. They used the language of high twist approach. And later, I also managed to solve for different cases, not only final state radiation relevant to jets, but also initial state radiation for Brilliant, or even the case where the Parton propagates without explicit hard scattering in the medium. So we kind of have all of those solutions, and we understand how the radiation depends on the medium properties and how it depends on the interference between the different sources of radiation. You see explicitly the minus sign. This is the Landau-Pomeranch-Knigdau destructive interference effect, which kind of changes the radiation pattern. Okay, so what is the next step? So this type of phenomenology has been applied for about 10 years. But if we work in the framework of having energy loss, we are somewhat limited. We don't quite know how to do result calculations, and we don't quite know how to rigorously do higher order calculations, such as envelope calculations. And if we want to make this connection, for example, high energy physics, we talk about higher order calculations in resonation, and they depend not on energy loss, they depend on the full in-medium splitting functions. And so starting around 2011, we started looking into extending those formalisms to full in-medium splitting functions. We first did this in the framework of soft collinear effective theory, which was supplemented to account for the interactions between the jet and the medium. We had to formulate two versions. One was for massless partons, and one was for massive partons. And here is the expression only to first order in opacity, the lowest non-trivial correlation between scattering centers for the case of a massive quark splitting. Now, it looks long, but it's not that bad, and it can be coded and calculated numerically. And then we also implemented this in the medium-induced evolution of fragmentation functions and made predictions for LHC. And here is the result of our predictions compared to data and to an energy loss approach. And it clearly gives a somewhat better prediction. Now, if we are going to go in the direction of increasing the accuracy of the theoretical calculations, we also have to worry about those higher orders in opacity. How about larger number of correlations between the scattering centers? And this is the work that we did most recently with Matt Sievert, but let me tell you what we knew about it going back to 2000. Of course, we derived any order in opacity contribution in the energy loss approach with bourgeoisie, and we studied it numerically. We studied it in like some very funny geometry that had an exponential fall-off, wasn't realistic at all, just to get a handle on what it does. And what we found is that even up to opacities of 5, 6 average number of scatterings, the series converges quite fast. You know, kind of at low Parton energies, this Parton energy 5 GeV, there can be, in this particular model, a factor of 2 difference. But you know, this difference is diminished quickly as we go to RIP and LHC energies. And in more differential quantities, such as the spectrum, the difference can be 30%, and if you look carefully, maybe it's about 50%. So clearly, if we're going into the direction of more accurate calculations, we should be able to calculate higher orders in opacity for the case of medium-induced radiation. So this is what we did with Matt Sievert. We formulated a framework which is quite generic, can work for cold nuclear matter, for the EIC, as well as the QGT. We isolated the transport properties in the medium in universal medium-mediated interactions by gluons. And we also looked in the region where the formation length, the splitting time for the process can be on the order of the mean free path, can be on the order of the size of the medium. We did not assume any particular hierarchy. We just went forward and calculated it. What we did neglect is collisional energy losses. These are sub-iconal interactions of the following type. The technique that we used is what Matt suggested, Lightcone wave functions, which is very often used in small x calculations. And this is how it works for the case of splitting in the vacuum. This is the Lightcone wave function, the square of it with the appropriate averages is the splitting function. And one thing that I found very satisfying is that this way you can calculate simultaneously both light and massive Parton splittings. We didn't have to come up with 2 effective theories to do that. And so, of course, we checked that this agrees with the splitting functions in the vacuum. Now, when we go to the medium, let's take a look at how one additional correlated scattering looks like. These are the diagrams, forward-cut diagrams, that contribute to this. We call them direct or single bond diagrams. We have interactions in the amplitude and the conjugate amplitude. And here is a typical expression for one of those diagrams. We have the propagators, which are encoded here in those Lightcone wave functions. We have the interference phases, the LPM effects, and these are energy differences. Those are virtuality changing interactions in the medium, which are also common to the propagators and the interference phases. We can do the same for the other type of diagrams that contribute to the same order, where the 2 interactions are on the same type, on the same side of the cut, and we call those double bond interactions. And here is a typical example. It kind of looks similar. Now, with this calculation by itself, we already recovered the previous results by Ovanessian and Tringer. We have full agreement for both massive and massive splitting functions. We also took the soft gluon emission limit, and we recovered the results by Julassian collaborators. And what's important here is not that we recovered known results, but this is what is the kernel for the evolution for building higher order correlations in opacity. So here is how we did it. So now we are going into the new stuff. One of the complications when we have QCD and interactions and diagrams with multiple legs is color. And what we wanted to show is that the color is not entangled. It gives us a homogeneous structure. What this means is that after we do the calculations, we ultimately have a multiplicative factor on top of whatever color structure we had before. we don't have plus terms and proliferation in power. We only have this in terms of kinematics. We then classify the interactions, all of those diagrams that I had, into. So this would be n plus n order in opacity. So how do we build it from n minus 1 order in opacity? We classified it into final state interactions after the splitting, initial final interactions before and after the splitting, and initial interactions. And so now we have what is a matrix equation. We can write down a recursion relation in this matrix form for all of those components which contribute to the final radiative spectrum. From the calculation that I showed explicitly, we can identify the form of those evolution kernels in the matrix, this upper triangular matrix. We can also identify the initial conditions. That's the second thing that you need when you have to solve an equation, an iterative equation. And so this is the simplest kernel. It's kind of, one-liner, and the most complicated kernel is quite a bit longer, has 8 more lines, but kind of the structures are relatively straightforward. Now, we went forward, so what do? We went forward and then calculated, presented exact results to second order in opacity. We wrote a mathematical code that can solve this evolution equation with the relevant initial conditions, and also presented the results. And so here is how it starts. It has propagators encoded by the Lightcone wave functions. It has color factors. We have interference phases. It's simply a long result. It's 9 pages because it is exact. We treat exactly the color and the kinematics without any additional approximation under the ICON. Okay, so we did this in the first paper just for the case of quark to gluon splitting. Well, we have like 4 splitting functions in order to incorporate them in evolution and higher order equations. And what really helps is to see that the topology of the splitting is exactly the same. So what we have to work out are the differences in the Lightcone wave functions encoded here. And we have to work out some different color factors. And pretty much this table encodes all the results now going from one splitting function to all 4 possible splitting functions. And we are done. So for all practical purposes, this is now a solved theoretical problem. Well, it's solved, but is it useful? I mean, a natural question to ask is, you just told me that it's 9 pages. Can you really do anything about it? And so for this, we will turn out to our numerical colleagues, our numerical experts. Well, the first thing that we did is, well, we didn't do it for the electron-ion collider. I mean, for immediate applications, there's a wealth of data from the heavy ion collider. And we did this for the case of a quark-gluon plasma. We did it not in a simplified Bjorken expansion model, but using full viscous hydrodynamics given by the Vishnu package by Chun-Shan and collaborators. And so this code, we started developing this code a long time ago, and even in the simple case, it took quite long, like 3 days, to obtain numerical grids for those splitting functions in the medium. We went from this simplified description to a full hydrodynamic description of the medium. And if I can do this for a medium that not only has a spatial profile, but also its transport properties change in time, I will clearly be able to do this for the EIC, for nuclei. Well, the improvements in physics led to some differences in the overall normalization, the strength of the medium splitting functions, and this is what we are going to use. So the way in which the code, however, was sped up. Let me go what we did with the code. So it would run even longer with hydrodynamics. So we spent quite some time restructuring it and shortening it, which led to a 20 times speed improvement. We made a better incorporation of the medium in the code, 2 times speed improvement, and efficient on-node parallelization. We were relying on the tuba parallelization itself, which turned out to be terrible. You can throw cars at it and it does nothing for you. But if you brute force parallelize it, you obtain near perfect scaling with a number of cars. So 18 days became 1 hour. So now, for all practical purposes, I can calculate sets of splitting functions and implement them in calculations. And that's what we did. Now I told you that the splitting functions are those fundamental ingredients that drive higher order and recent calculations. And due to soft collinear effective theory, it was realized that you can even measure them directly. How do we do that? Imagine that we reconstruct a jet, and then we go inside the jet and sequester the energy into two prongs. We eliminate soft radiation. We kind of require the prongs to be hard. This is called soft grouping. Grooming, these are technicalities. We can even require separation between the two subjects. And if you think about it, this is directly the splitting function. You are directly measuring the two splitting functions. And if we plot the ratio between heavy ion and proton collisions, and we directly plot the same lowest order non-trivial calculation, this is what we predict, and this is what is observed by the experimental data. So we have good confidence that those in-medium splitting functions are indeed directly probed and relevant. Well, that was first order in opacity. So now let's go to this. Yeah.
This effect in the is not so big, right? In having calculation, which you expect the medium effect is much stronger than, let's say, code QCD. So,
sorry.
Do you expect this to be observable? Can be observed in the EIC? Because
well, at the EIC, we're going kind of to lower energies. Remember that the lower energies effects are larger. Now, the densities are different. I'll show you if I get to it, because I already got 10-minute warning. I'll show you not for a different substructure observable. But let me kind of go through this really the implementation of the long calculation. So we want to evaluate now numerically second order in opacity, see what the effect is. Difficulties, large number of evaluations, long expressions, additional three-dimensional integration, expected to be slower, but still we kind of hope that it will be done within a day. And to not make mistakes, we directly export it from mathematical C++, so that we don't make typos in coding. And so here are the preliminary results that we now have with Matt Sievert and Bara Myon. Now, what is called lowest order is the lowest opacity. What is called next to leading order is the second order in opacity corrections. Those are not strictly lowest order next to leading order. I think this is something that Matt miscommunicated to Bara. What is also shown is not simply the splitting intensity as a function of x, is the fully differential dn dx decay curve, including angular separation at a fixed k. And in the case of quarks, it is done for a heavy quark, just to show that we can do it. Of course, this is a gluon splitting, and the mass plays no role whatsoever here. It was just kind of put. So what do we see? We see that the second order in opacity results, we see that the series is really well behaved. The second order in opacity results range from practically nothing to maybe, about 50%. But this 50% is just kind of due to the fluctuation in the Monte Carlo. It's just because the numbers are so small. For all, and of course, this does not contribute to trading these orders of magnitude down. So for all practical purposes, the second order in opacity gives us 10% change relative to the first order. And now this gives me a lot of confidence why the first order in opacity results work well, and then we can kind of go and do even more precise calculations with that. So here we've done something for the electron-ion collider. I said that we can code them for cold nuclear matter without expansion, and I have done that. I have done it for only first order in opacity. Second is not done yet. The technique that we used, we wanted to see if it's going to work for the Hermes data, is full in-medium splitting functions. We didn't fiddle with energy loss. We just kind of added medium-induced evolution on top of the vacuum one. And this approach was shown to give good description at the LHC. Let's see how it works in deep inelastic scattering. We also did not fit Hermes data. What I did is I used transport properties of nuclear matter, which I have constrained before over years from the Cronin effect, coherent power corrections, or initial state energy loss, which is relevant for the E906, for the Darwinian process. We look directly at the modification of the fragmentation functions, and kind of, if you want to multiply by a to the 1/3 the nuclear thickness, and call this a saturation scale, I'm plotting this value for quarks, how a quark will see the nucleus, and how a gluon will see the nucleus. The difference is the Casimir. If you want to know what is like the total momentum transfer that you can get. And here is what we obtained. We combined this with the full next living particle, and we presented the results. Now I have this figure only in a PDF form. So yesterday I had to very carefully look and put the Hermes pion data just by hand. I apologize. So once we actually get to make the figure, but I've tried to do this accurately. And you see that for the lightest nuclei, it kind of lies on the upper edge of the band. Perhaps the theory overpredicts this a little bit. For the heavier nuclei, such as xenon, that would be the blue band, kind of the data is compatible with the upper edge of the band. And once again, this is no attempt to fit data in any way. So we will, of course, do this. We'll try to get better constraints, the best constraints, but this is what we got. And finally, if we push forward and start looking at jet production, and this is jet production, for example, at 140 GeV EIC, we went and derived what the modification would be. To look in Hadron production inside jets, there have been recent developments coming from SCT in terms of a semi-inclusive fragmenting jet function. A factorized cross-section can be written as, you know, the standard convolution, you know, the hard part, and this is the object that takes into account simultaneously jet production and hadron production inside jets. It obeys certain evolution equations. These are big-like evolution equations in 2 scales, and we can derive how the medium modification enters. Here are some example diagrams, and it comes in terms of the lowest non-trivial order as those terms. The first part will give you suppression of jets, suppression of jet cross-sections in semi-inclusive DIS, and the second one would be the modification of the hadrons inside, and we have to combine them. And these are our ultra-preliminary results. What you see here is the modification is a function of the momentum fraction of the hadron inside jets, for jets in the following PT regions. And you see that the modifications are significant. They can be as large as 50% to a factor of 2, and this is quite comparable to what we've seen so far in heavy ion collisions. So I wouldn't say that the modifications that we expect at an EIC, I hope will be measurable, rather comparable, maybe not nearly as strong as in AA collisions, but, you know, half the strength or so.
So the PT range are the jet energy range? Or the...
No, that's the PT range,
Okay.
not the jet energy range. Right? Jet energy range is integrated over. Yeah. We also didn't include in this calculation at lower PTs, and PT5G is not a high PT for this purpose. At those PTs, you have the resolved top production channel, which we did not include. But again, this is just to show what we can expect, you know, somewhat quantitatively. So let me not go into detail, but there are other opportunities, like even without nuclei, that one can explore. Maybe some of you are aware that there are various extractions of alphas for various event-shaped observables in E+, E-. And there is a tension between those extractions, about which was the most obvious. This one, I think, and that one, I mean, it's like it's clearly more than several sigma discrepancy. And one possibility is to use data, event-shaped data from semi-inclusive elastic scattering to actually further constrain alphas. This is a place where an electron-ion collider will help. Just because here I had higher energies, if we do theoretical calculations of event-shaped observables called one-jetters, again in the language of SCT, the theoretical error bars here are the smallest and at higher energies, and as we go down in energy, they become a bit larger, but still, they're reasonable theoretical uncertainties, and hopefully this can be incorporated in the analysis of how fast in the future. So finally, this brings me to my conclusions. So I think there are tremendous opportunities for jet physics in EP and EIC collisions that are not fully explored yet at the electron-ion collider. On the experimental side, I mean, the EIC can help us determine the transport properties of nuclei, radiation lengths that may be the shortest in nature, and this is a multi-year physics program. It also resonates to a large part of the nuclear physics community that now, experimental and theoretical, that now works at the LHC. Now, on the formal side, what I showed you is that we have techniques to calculate full in-medium splitting functions to any order in opacity, and we have explicit results in numerical implementations. These require new theoretical techniques. These are techniques that are common between our field and high-energy fields. Those are not simply energy loss models. These are based on factorization, evolution, and semi-inclusive jet functions and fragmented jet functions. We can validate the approach against existing data, but of course our emphasis is looking into the future of jet physics. And we're also looking on the numerical tools for jet simulations in reactions with nuclei. By numerical tools, I do not mean Monte Carlos. I do mean like those evaluations, precise evaluations that I talked about, as well as the higher order calculations. Thank you.
Another question from ignorant guy. I understand that the transport coefficient is a very useful observable from the point of view of experimental point of view, because it's very sensitive to different ingredients. But I'm wondering if there is any other observable in this business that can help. Is this the only one that have?
Well, it's like the other quantities are, as I said, radiation lengths, scattering lengths of partons in nuclear matter. I'm quoting the transport coefficient because it's become customary to quote it in the case of heavy ion collisions. Personally, I'm not a big fan of the transport coefficient. The reason is very simple. In heavy ion collisions, as I showed in this hydrodynamics, not only do we have like spatial variation of the density and temperature, and it's the temperature that drives transport coefficients, but there is also temporal variation. So when do you quote it, right? The transport coefficient changes as a function of position and time. On top of that, certain groups, there are logarithms. If you interpret it as scattering, some groups include logarithms of the energy. So I can quote one transport coefficient. So it's a bit of a tricky business. So for this reason, when we do calculations, I tend to formulate them in terms of scattering lengths, momentum transfers from the medium, which are a little bit more robust than any logarithm which would arise from scattering I calculate explicitly. But in addition to summarize, in addition to transport coefficients, scattering lengths, radiation lengths, I think are quite useful. The situation is a little bit better in DIS, because at least we don't have the extension to have decided time-dependent complication.
I have a question. Maybe I will start with just a comment on what you just said. I think there is one more thing with DIS is that you actually measure the transverse momentum, and especially in the view of transport coefficient in terms of transverse momentum given to the quark. You showed a lot of comparisons with Hermes data, but you didn't show any comparison with their data on transverse momentum.
Yes, they have measurements.
So they actually measure this Q hat, so we more or less know if you're in a framework where Q hat is, you should reproduce that as well.
Yes, and well, the reason for which I did not show it is, so to summarize, if we interpret this Q hat, transverse momentum transfer per unit length, multiplied by length squared, we get transverse momentum squared. And so Hermes also measures what is the enhancement in transverse momentum due to nuclei. And this enhancement is on the order of 0.05 GeV squared. So how can we get 0.05? The difficulty is associated with it because one has to multiply the broadening, Partonic broadening, by the fragmentation fraction squared, right? So if you got broadening which is smaller than that, you are bad. If you got broadening which is somewhat larger than that, I think you're fine to an extent. If the broadening is way too big, I think it's still a problem. So I do think that Chinyas is a little large, as I said. I think that what Herriot did, too small. What Herriot did is too large. I think the truth is somewhere in between. And that's exactly what we can start with, more precise measurements.
But I have a question because at the end of your calculation, you didn't quote that, you just made a link directly with the saturation. Could you explain a little bit more about
Yes, so the Q hat is, let me go. So what, when did I do that?
Yeah.
Okay, so what Q hat is here is the zeta squared, right? You know, it's like for me free paths of order Fermi to Fermi. So zeta squared is 0.1 GeV squared. So you know, kind of Herriot extracts 0.7, Chinian extracts 0.04. I've constrained this to other processes. As I said, I plugged it in. Okay.
Other questions or comments? It's not the case, so let's thank Ivan again. But I think unlike yesterday, we have the second talk and then the coffee.
There's no coffee outside.
Yeah, it's coming.
Coming, not yet, so.